Hello and welcome to a new episode of What, Why and How. In this video, let us discuss about Markov property and Markov models. When you toss a coin, you know that the probability of head or the probability of tails is 0.5. But this doesn't mean that when you toss a coin two times, say first time you have head, it doesn't always means that the second time is should be tails because the probability is 0.5. This 0.5 is nothing but a steady state probability. That is, if you tossed a coin n number of times, that as n tends to infinity, that is the more number of samples that you have, the probability of heads and probability of tails converges to 0.5. In general, the weak law of large numbers states that if you have n independent samples and as n becomes bigger and bigger, that is as n tends to infinity, the sample mean converges to the population mean. That is, in this case, as you toss the coin more and more number of times, as the number of samples becomes very large, the probability of head and tails becomes zero point 0.5, which is the steady state probability. However, the important term that one has to note is the samples have to be independent. That is, the outcome of one coin toss should be independent of the outcome of the previous coin tosses. However, Markov had this question on whether this independence is a required condition in order for the mean of samples to reach a steady state. Markov created a way to describe how random systems or processes evolve over time with dependency involved in them. What is particular about Markov systems is that it is modeled as a sequence of states. That is, at each time step, the system is in a specific state, and as time progresses, the system moves from one state to another state. If we take the coin toss as an example, head and tails are the two different states in which the system can be present. And as you toss the coin, that as the time progresses, the system is either in one of these two states. It's either head or tails. And what is particular about this Markov system is that as the system transitions from one state to another state, that is, the coin toss experiment, as you toss the coin and as you get these outcomes of head and tails, the outcome at any particular time t is only dependent on what the previous outcome was at the time t minus 1. This outcome at time t is completely independent of the path followed to arrive at this particular outcome. That is, it is independent of what the outcomes were at the previous time periods except for the time period t minus 1. This specific property is called as a Markov property, which states that at any time t, the probability of outcome is only dependent on what the state of the system was at the previous time t minus 1, and it doesn't matter what the states prior to that were or how we reach that particular state t. Putting all these characteristics together, Markov was able to prove that as long as you can reach all the states from each other, the probability of moving to a particular state will converge to a single steady state value in the long run. Coin toss example, you have two states S1 and S2, which are heads and tails. And as you toss the coins, that is, as you move forward in time, you can transition from one state to another state, or you can stay within the same state. That is, your next outcome can be tail, or your next outcome can remain head, or if your current state is tail, next outcome can still be tail, or your next outcome can be head. So the transitioning through one state to another state kind of creates a chain, and therefore this is also called as a Markov chain. Creating a model that encodes these dependencies is a more realistic way of representing the real world. Let's take an example from football. Assume that you are an analyst assigned to help a goalkeeper in saving his penalties in his next game. Now, when a penalty taker takes a penalty, he can either hit it straight, or he can hit it to the left, or he can hit it to the right. You want to help the goalkeeper in predicting where the penalty taker would hit his penalty next. So you want to model this particular system as a Markov chain with three different states. State 1 is left, state 2 is straight, and state 3 is right. And you have made an assumption that wherever the penalty taker is going to take the penalty next is dependent only on the direction in which he has taken his previous penalty. Therefore, you can model this as a Markov chain. Assume that you have done your historical analysis and gathered this data for the penalty taker. So what this table tells you is that if the penalty taker has taken his previous penalty to the left, then there are 10 instances he has taken his next penalty also to the left. 5 instances where he has taken his next penalty to the center, and 10 instances where he's taken the next penalty to the right. Similarly, if he has taken the previous penalty to the center, then there are 5 instances where he has taken his next penalty to the left, 3 instances to the center, and 7 instances to the right, and so on. So these numbers, so overall you have gathered 50 data points, and from this you can calculate the corresponding probabilities. Putting this in matrix form, it looks something like this, where this matrix, each element gives the transition probabilities of transitioning from one state to another state. And therefore this matrix A, it is called as a transition matrix. Now in order to visualize this, we can put this as a directed graph which shows you the corresponding Markov chain, which each arrow represents the transition probabilities from one state to another state. For example, the probability of transitioning from left to left is 0.4, and that's what this arrow shows, the probability of 0.4. Similarly, the probability of transitioning from left to straight is 0.2, and that's what this particular arrow shows, and so on. Now, using this transition matrix and the corresponding transition probabilities, there are a few things that the analyst can answer. For that, he needs three things. What is the start state? What is the end state? And how many time steps? Let's see the first question. Given that the penalty taker has taken his previous penalty straight, what is the probability that he takes his next penalty to the left? So when we say next penalty, the number of time steps is 1. This is pretty easy to answer. It can be directly answered from either this transition matrix or from this directed graph. So what is the probability of transitioning from straight to left? It's nothing but 0.33. Now let us increase the number of time steps. Given that the penalty taker has taken his previous penalty to the straight, what is the probability that he takes his second penalty from now to the right? Second penalty from now, so the number of time steps is 2. Now how are we going to answer this? Let us look at this directed graph. There are multiple ways of reaching R from S in 2 time steps. Let's list out the paths here. Path 1, he can go from S to L and then L to R. That is, he can, given that he has taken the current penalty to the previous penalty to the center, he might take the next penalty to the left and then take the penalty after that to the right. The second path is from S, he can take the next penalty also to the center and then take the next penalty to the right. The path 3 is he can take the penalty from center to the right and then again to the right. In all these 3 paths, in time step 2, he has taken his penalty to the right. Now what is the probability from going from S to L in one time step? It is 0.33. And from L to R, it is 0.4. In path 2, the probability of going from S to S is 0.2, and probability of going from S to R is 0.47. In path 3, the probability of going from S to R in one time step is 0.47, and the probability of going from R to R is 0.2, which is this. So putting this all together, the probability of going from S to R in 2 time steps is nothing but the combined probabilities of path 1 and path 2 and path 3, which is 0.33 into 0.4 plus 0.2 into 0.47 plus 0.47 into 0.2, which is equal to 0.32. So the probability of going from S to R in 2 time steps is 0.32. Before going further, let's answer one more question. Given that the previous penalty was taken to the center, what is the probability that he takes his second penalty from now to the left? And if you do the calculation, this will come out to 0.34. Now, is there a value? Now, is there an easier way to calculate these probabilities at different time steps? Let's see what happens when this transition matrix is multiplied with itself. Now, we have the transition matrix A. Let us see what the value of A square is. Let's use Python to calculate A square. So import numpy and matrix power from numpy. This is our transition matrix Tm, so on. Now let's calculate the second power of the transition matrix. We get 0.346, 0.32, 0.334. So this is the value of A square. What you notice here is, let's compare the numbers in this matrix with the number probabilities that you have that we have calculated here. We see that the probability of a right penalty kick in 2 time steps, given the previous penalty kick was straight, is 0.32. And if you look at this matrix, given the previous penalty kick was a straight, the probability of the right penalty kick in 2 time steps is 0.32. Similarly, given the previous penalty was to the center, the probability of a left penalty kick in 2 time steps is 0.34. And that's what this matrix also says. Given the previous penalty kick was to the center, the probability of the penalty kick is to the left in 2 time steps is 0.339, which is 0.34. So essentially, what raising the transition matrix to the power of 2 basically gives us the transition probabilities in 2 time steps. So this 0.346 would represent the probability that given the previous penalty kick was to the left, the probability of a left penalty kick in 2 time steps is 0.346 and so on. And it doesn't stop at the second power of the transition matrix. As you increase the number of time steps, and this doesn't stop at the second power of the transition matrix. If you want to figure out the probabilities of the third time step, just take the third power of the transition matrix and that will give you the transition probabilities at different time steps. That will give the transition probabilities at the third time step. As you increase the number of time steps, for the fifth power, you slowly start to see certain pattern. You see all the columns have been approaching a specific steady state value. We take the 6th time step. These are the values. 7th time step. You see that the numbers are almost same at the columnar level up to the 3rd digit. We take the 8th time step. We take the 15th time step. You see these numbers have now reached a steady state value. That is, in all the columns, you see the number is exactly the same. If I copy over this matrix, you see that after certain number of time steps, these probabilities do not change anymore. if I go to 16, if I go to 20 time steps, the probabilities remain the same. What this tells me is that the probability of hitting a penalty to the left is always the same, irrespective of what the previous penalty kick was. Similarly, the probability of hitting a penalty straight is always the same, irrespective of what the previous penalty kick was. And similarly to the probability of hitting the penalty to the right. These are basically the steady state probabilities of probability of penalty hit to the left is 0.343, probability of penalty to the straight is 0.305, and probability of penalty to the right is 0.351. Therefore, even with dependency encoded into this particular system, the probability of a particular state after enough number of time steps have reached a steady state value. And these are the specific probabilities. And this is what Markov wanted to prove all along. In all these examples that we have earlier taken, we have the previous state given to us. Now, given that we have these steady state probabilities, we can answer a different kind of question on what is the probability of next penalty to the right in one time step, which will be nothing but probability of the previous penalty to the center into probability of next penalty to the right given center plus probability of previous penalty to the right into probability of next penalty right given previous penalties to the right plus probability of the penalty to the left into probability of next penalty to the right given left. Putting the numbers from transition matrix here, we can easily answer this question. Hope this gives you a good understanding of what Markov chains and Markov property are and helps you understand in next time when you come across someone saying a Markov property, you would be able to relate to this example and understand the concept much better. Thank you.